Hello and welcome to our next Shell Eco Marathon virtual learning session with Altair Engineering. And welcome back to those of you who have joined us in previous sessions. My name is still Norman Koch and I'm the Global General Manager of Shell Eco Marathon. I would like to start off by thanking all of you for your flexibility and understanding as we evolve the Shell Eco Marathon program due to the COVID-19 situation. As the situation continues to still change, the safety and health of our Shell Eco Marathon participants and organizing teams remains our top priority. And given current status, we're really excited to have you all here with us in this new digital environment to kick off our virtual learning sessions, all from the safety of your homes. Today, we'll be hearing from Paul Over from Altair Engineering about lower energy consumption and better performance with optimized aerodynamics. Altair is a global technology company that provides software and cloud solutions in product development, high-performance computing, and data analytics. Altair has been supporting Shell Eco Marathon by supplying licenses, training, and support for Altair HyperWorks to teams competing in Shell Eco Marathon for 4 years. Paul is a master student of theoretical mechanical engineering at Hamburg University of Technology. His focus is on fluid mechanics and aeroacoustics. He led some of the CFD activities for thermal management and race aerodynamics at the Formula student team E-Ignition in Hamburg. After an internship at Altair in Sweden to create the ultra-fluid, he continues to work as a student ambassador for Altair. And believe it or not, in his free time, he loves fluids as well. He enjoys free diving, fishing, and does all kinds of water sports. So welcome, Paul, to the program. We look forward to hearing from you in just a few moments. But before we get there, I'd like to make sure that the session gets as interactive as possible. So if you have any questions throughout the presentations, please go to the website menti.com on your browser and enter the code shown below on the screen. Or on Menti, you can only enter your questions. You can also see what questions have already been asked, and you can give the ones you think are most relevant for you a thumbs up so that they rise to the top. If by any chance you have problems with accessing Menti, you can also type your question in the comment box on the right of the live stream once you're logged into YouTube. And then at the end of the presentation portion of this live stream, Paul will be answering your questions, and make sure you ask him really good and really tough questions so that he's really stretched a bit. Don't forget, please, this is a live stream, so if we should encounter any technical difficulties, please bear with us as we fix the problem. We will get to you as quickly as we can. And I guess that's all from me now. I will go over now to Paul from Altair, who will officially kick off this session. Paul, the floor is yours.
Thanks, Norman, for this introduction. Guys, this is not the Eco Marathon we all wanted to have, but now you can take this time to go further in development, and from my side, really warm welcome to this. At this place, also a big thank out to Shell to put in this place or put this webinar and organizing all the stuff. The last days you already had the opportunity to have a look into analysis and topology optimization with Altair Inspire, hosted with my colleague Eric. And today we're gonna have a dive into modern CFD and especially into lower energy consumption and better performance with optimized aerodynamics. Let's kick off the session by starting directly into some slides I prepared. Mainly what connects us all in engineering, or maybe a big part of engineering, is motorsport. Motorsport is a world of challenges. Automotive companies are continuously under pressure to set new lap time records. They develop and deploy new technologies and to keep on breaking their own records. Apart from this huge thing are race cars. And those are characterized by highly developed assemblies, engines, chassis, and of course, external aerodynamics. The same yields for Shell Eco Marathon. Every year, all the teams compete on events in ultra efficiency classes. Besides the drivetrain, the kinematic, and the software, the external aerodynamic design is an essential part to reach ultra efficiency. Let's break it down. Let's start from the beginning. What is external aerodynamic for automotives? The external automotive aerodynamic directly lead to forces. First of all, the car or the vehicle is surrounded by air which flows over the vehicle. This air leads to forces acting on that vehicle. Besides lateral forces and moments created due to crosswinds or other natural environment conditions, the greatest interest is in lift and drag. Those ones you see here on the right picture, in the picture on the right, indicate with the blue arrows with lift and drag. The drag. The drag is a force which acts against the driving direction. It's related directly to fuel consumption, the maximum velocity, and the overall range. The lift, on the other side, is a force which pushes the vehicle to the ground. It's directly related to driving stability and cornering behavior. To compare simulations from different kind of vehicles, the two equations below formulate coefficients which can be used. In these formulations down here, the forces made dimensionless and transformed into a coefficient of drag and a coefficient of lift. And those now are able to compare under every different kind of case. But now, to be ultra efficient, what is the main thing when we look back on the options the two forces included or the results they pushed? The drag is standing out with the fuel consumption in the range when it comes to ultra efficiency. So the question is, where does it originate from? Can those regions be identified? I just prepared a slide where I just pointed out some sensitive region in rough proportion. Of course, some region can be pointed out, but in general, you can divide them by the following. 40% of the overall drag is gained by proportion and shape of the vehicle, 30% of the wheelhouse and wheel, and 10% is around in the internal flow. The underfloor or the underbody of the vehicle is determined 20% of the overall drag. When it now comes to the Shell Eco Marathon vehicles, I think the most important might be the proportion and shape, and of course, wheels and wheel housing. But why do I am talking all the time about aerodynamics and external aerodynamics? Let's have a look on that. So I just bought it's a good slide here to get some numbers running. On the right, you see what on the left, you see what aerodynamics really is about. On the right, you have a nice table with some numbers in there. First of all, EUDC and NEDC, that stands for emission test cycles motivated by the automotive industry. But that's not the important part. The important part is when you imagine you're driving in the city. So we are in the first line of the table, and now we're changing the coefficient of drag about 0.01. The fuel consumption changes about 0.01 liters per 100 kilometers. Related change that would be in related change in equivalent mass about 6 kilograms. Okay, it's fair enough, not that much. But now imagine you drive fast and you drive way fast, so 120 kilometers an hour. And now we change the drag about the same amount. Then the fuel consumption changes about 0.09 liters per 100 kilometers. When we now relate it to the equivalent mass we gain, it's about 129 kilograms. And I think that's quite a lot. Okay, now we got all this part together. We got this motivated. Now the question is how to optimize the aerodynamics of the vehicle. Optimizing the aerodynamics of the vehicle is quite a difficult task. It requires experiments, theoretical knowledge, experimental data, maybe for wind tunnels, simulations, and to achieve an efficient, balanced, and good aerodynamic setup, all of this should be understood in a good way. Today, my mission is to give you an ultimate insight into lower energy consumption and better performance with optimized aerodynamics. Let's have a look what's this about in detail. So, like I already said, optimizing the aerodynamics of vehicles is a difficult task. So we have to take a small look in theory. That's where we start first. I like to dive into some basics to get your theoretical knowledge back up and running. Of course, simulation nowadays are an integral part of vehicle development and thus an integral part of everyday engineering's life. So we'll dive into some practical part afterwards, where I'm going to show you some brilliant software which makes it intuitive to set up a simulation for your own Shell Eco Marathon Racer. At the end, I prepared some results I'd like to show you, and then we talk about some common ways to process your simulation in an efficient way. And after this whole session, you should be able and ready to start with ultra-fast transient simulations. Just the last point here, if you have any questions that are coming up during the presentation, please use Menti, blinded in below now, dial in the code 220330 and you're ready to go. We will try to handle all of your great questions in the end when we switch back to normal in the studio, and then we have a small discussion and Q&A session. But right now, let's kick off the ground vehicle aerodynamics lecture part, where we have a look on the reality and the virtuality. So, ground vehicle aerodynamics can be basically divided into a real part, what we're gonna have to speak about now. And reality, okay, this is not really the reality. This is just a schematic sketch of a car. But let's try to understand what is happening in the reality. Imagine you sit in a car and you're driving along the roads, and the air in front of you, first of all, is then in totally stationary and total equilibrium. The car moves towards that air. The air flows around the car, and of course, at the front bumper, the air hits the car normal to its surface. The velocity of the air goes to zero, and the pressure increases to its local maximum. The air above the front bumper gets pushed up a little bit. The velocity rises and the pressure decreases. The effect of kind of suction appears. The same yields for beneath the car. The air gets pressed through the small gap between the road and the car itself. Also, the effect of suction appears. Behind the car, it looks way different. There's flow separation. The flow separation mainly introduces a lot of drag. But this is only named one thing which could introduce a lot of drag. Let's dive into the real reality and have a look where the drag might be coming from. So here we have a real car, a Shell Eco Marathon Racer. And I just pointed out some region of interest in a more detailed way, and we like to speak about that. The percentages given here on the side, they are related to the overall drag, and they can be caused by just having an unoptimized design. For example, taking the radius at the front bumper into account, it causes up to 2% of the overall drag. The roof contour, listed at 0.5, has an influence about 1% of drag. The diffuser, it says, itself nearly shows no drag at all, because it's low installation drag device. When we now see that all the numbers are placed behind at the underbody or underfloor of the car, and we remember the numbers from the beginning, how much energy you could save. Then the question is how to save it. And there is where we come to the underbody itself of that car. The underbody can be separated in two parts, the ground clearance and pitch, and as well as the underbody covers, which determine the flow beneath the car. Talking about the pitch. Increasing the pitch, so lifting your vehicle's nose up, like in the rider picture, it leads to increase of drag and lift. If we have a negative pitch, nose down, it creates a kind of pseudo diffuser effect on the entire underbody, which reduces the drag and lift. When we now change the ground clearance, so the smaller the ground clearance, the lower the drag. Regarding the lift and the ground clearance, there's a kind of optimal ride height for the car. It's a really nice tool on the screw where you can play around when it's about balancing the aerodynamic forces on your vehicle. Coming to the underbody covers, covering the underbody to reduce its roughness and therefore reduce the drag is the main goal of those covers. If possible, the underbody should be covered from starting at the front as far downstream as possible. But look out, attention, there might be thermal requirements, cooling transport, and other constraints. Here at Shell Eco Marathon, you don't have that much underbody. The whole car geometry is one in itself. So that's why I like to speak about a rear diffuser, which may come into account for you. A rear diffuser is one special device, and as I already said, the installation drag is close to zero. This rear diffuser can build into your body geometries, and a well-designed diffuser can help to reduce drag and also lift. In general, you can say that longer diffusers are more efficient, but they only work well if you have undistributed upstream flow, as found on many Shell Eco Marathon vehicles, so quite good. You should have definitely a look into this. Another big thing are probably the wheels. So when speaking about Shell Eco Marathon vehicles and taking a look at pictures, wheels are quite obvious. And the wheel is super important as well. There is happening a superposition of flow around the car and flow around the wheels, leading to a complex flow in itself. When now we drive forward and add the wheel rotation, we add additional effects so that all over the 30% of the car's total drag is caused by the wheels or the wheelhouse. So where to attack? What to change? The tire and rim size could be altered. Maybe a closed wheel setup is more suitable to lead to lower drag numbers instead of an open one. Do experiments and better run simulations to really achieve a good setup for your wheel placements. Besides this, we also need a little bit more external aerodynamic parts to get the vehicle running. The last point is to speak about in and outlets of your internal flow, how to design them. Especially interesting when it comes to cooling your fuel cells, batteries, or even engines. A proper design can save a lot. By using the local momentum added in the radiator or in the outflow, it might even be possible to reduce the installation drag close to zero of these in and outlets. So that's really interesting. Let's look at one example here. On the right, I showed up some typical car sketches and some bar diagrams. Version A shows a classical passenger car. We have high drag, you see down the bar diagram, and a good mass flow. Okay, the air is entering right in driving direction, against driving direction. And for example, in figure C, we're using the pressure regions to support. So we gain a lower drag and the mass flow is nearly the same. What I really like to point out here is that inlet and exit with the phase in normal stream direction does not necessarily include low drag values. So be creative and experiment and use the local flow field to really get a good result. As I said, interesting is also the point when it comes to the outlets, the exhausts. The same important yields for them. Generally, they should be placed in low or good pressure areas as well. But attention here on the outlets. When you have an outlet, you increase the local boundary layer thickness and therefore the likelihood of flow separation on the surface attached to it. And as we already had, flow separation means more drag. Let's dive into some examples as well. On the right, again, you see some diagrams and sketches I put on here. Not diagrams this time, it's more sketches. But in A, you see a conical sheet metal, just a simple exhaust for maybe your battery cooling. The influence and pressure and drag is, I would say normal, and it's a good workaround. But there is a better way to do it. For example, with version D. Version D shows a flush exit, which has way smaller influence. So it's nearly no influence in pressure and less influence in drag. And if you place it right, you can even use the fact that it improves momentum transport to the boundary layer. This is how the reality looks like. And due to that we got that roll up now. Now it's interesting, and there's a question, how does it look when it comes to simulation? And why should we use even simulation? And what are the common methods? These are my questions you ask yourself now. And to motivate it, I just put up some numbers here. So why should you use simulation? First of all, money. Of course, the wind tunnel is expensive, the prototype is expensive, the automotive industry spends a lot in these experiments, and therefore computational fluid dynamics would be a good alternative. But for you as a student team, a big point as well is there's no big tunnel at all. Or better to say, some of you, which may have one, they can't use it all the time to really have a dynamic iteration process. So computational fluid dynamics is a flexible and fast alternative to wind tunnel experiments, and CFD offers almost unlimited possibility for the analysis of the flow field. You can just do it at a computer, zoom around and have the pressure values as a total different location. In the wind tunnel, that's not possible. If you set up the experiment like this and then you think about having a different number or scalar noted or recorded, now gone. So that opportunity you always have using the computer. Coupled that CFD software with the computing power of today's computers, CFD makes it possible to develop complex aerodynamic components and further increase the performance of the vehicle without building and testing every design option in the wind tunnel. Let's have a look at what's on the market and what's really interesting about it. So right here, I just put down the most common ones. One's the Navier-Stokes, which also may be known from fluid dynamic classes or studies, what you already done in school. Or the other one is Lattice-Boltzmann. And the main difference between them is how they interpret the continuum. The graphic on the right summarizes those differences. Let's take a look at it. So when it comes to Navier-Stokes, it's a conventional CFD solver and it uses macroscale interpretation. It's up right in the corner there. The length scales are as we know them. It's millimeters or meters, and the continuum itself is divided in cubes and way more mathematically and logical. The Lattice-Boltzmann method, on the other side, is a particle-based method and uses mesoscale interpretation. The continuum is not divided in small cubes or voxels, it's divided into particles. And these particles or these length scales in the region or in this continuum are around the mean free path length, known maybe from quantum mechanics class. So the length where we have 100% chance where every particle has to collide with another particle. So we zoomed into the continuum way further. Just to round this up, there's also the microscale simulation, which would cover movements of atoms, but we exclude that point here in the webinar. In those both methods, the Lattice-Boltzmann and Navier-Stokes approaches, we use a finite volume method often to specially discretize the continuum. If we take now the comparison from the theoretical view we had here to a practical one, there are some more advantages which come into account. In the direct comparison of the method, both can be used to describe aerodynamics, so there is no difference at all. But there's still a lot to do, what we can point out. The Lattice-Boltzmann method is transient and explicit. The Navier-Stokes is implicit and mostly steady state. Due to that the Lattice-Boltzmann method is transient, we have way more accuracy and it's possible to design aerodynamics more exact, especially when it comes to high-end efficiency. It is even possible to look at aeroacoustic fluctuations in that continuum. In Navier-Stokes, when it comes to steady state, all transient informations are averaged and summed up into one single frame or shot of time. So it's not even possible to capture all effects. For example, the wakes around the tire, what we had the slides before. And not even, this is maybe a big advantage of Lattice-Boltzmann, there's also when it comes to mesh. Down here, you have some mesh examples shown up. Once the surface mesh for Lattice-Boltzmann, you see that it has really low requirements. The mesh is quite simple and not that detailed like the high-quality trias one, where we see that around the edges in Navier-Stokes we have small tria elements and we have a way more skew angle and the quality is way higher. When it comes to volume mesh, it's nearly the same there. Lattice-Boltzmann uses the finite volume approach, but it's a pure Cartesian grid generated automatically. Volume mesh and Navier-Stokes is way more complicated. It's also a finite volume method, but it's locally adapted, and there's a lot of transformation mathematics going on to really calculate on those grids. When we just compare the runtime in the last step for a transient simulation, Lattice-Boltzmann would probably run half a day. So we have fast turnaround times for design changes, because Navier-Stokes, for the same simulation case, it would take easily 2 days, depending, of course, on the hardware. Now you're probably all asking yourself, what really is this Lattice-Boltzmann method? Oh, let's jump into some details. So we have one equation. It's the Boltzmann equation. It is solved on a discrete lattice. The lattice is constructed out of the voxels, like here, that one on the right. So these small voxels or cube. The solving process is separated in 2 steps, the streaming step and the collusion step. In the streaming step, the particles stream in their determined direction. In the collusion step, the particles collide. New velocities get computed, and positive particle velocities are discretized in these 19 ones. So we don't allow any velocity here, only 19. And this is a step where we discretize in ultra. So this D3Q19 velocity set here says that we have 3 dimensions and 19 velocities for the particles to stream at. Due to this discretization, we keep the transient nature of the flow inherently respected. And physics behavior is determined still by the viscosity of the fluid only. Okay, just to round this up, let's have a small look onto the iteration process itself. And then I leave you to the more practical things, and we end the theoretical lecture one. The Boltzmann equation, upright one, here in the middle, It sets the recent and the equilibrium density of the particles into relation. In the collusion step, we already had it, the discrete velocities get determined. In the streaming step, they stream. And now the Boltzmann equation brings that into account. Based on the equation, we can determine the macroscopic moments, like velocity or density, directly. So the solution, which is covered by the Navier-Stokes equation, are also directly solved here in the lattice Boltzmann equation as well. Okay, let's sum it all up. We got low surface mesh requirements, tribal volume meshing, and we can do transient simulation, which should be even more interesting in regard of high efficient external aerodynamics. Now I just want to point out, if it was a little bit too fast, or maybe the slides have a lot of information on there, I know. You have any question during the last slides, use Menti and dial in the code 220330, and you're ready to go. We try to handle all the questions in the end with Norman from Shell Studio. Beside this, there's also the option I want to point out. We published the ebook, which summarizes all this theory and gives information about it. And you just have to have the read through there. You get even more, and you can read it through every time. Let's close up this lecture session and start into the practical part and have a look on the tools we should use to set up that simulation. Tailor-made tools, they should be used to follow this kind of simulation pipeline, which is always in this general way. The preparation process is the first process. There we start to prepare the surface, and that we will do in Inspire Studio. The pre-processing, the setup of the simulation, we do in Virtual Wind Tunnel. The solving in UltraFluidX, and the last, the post-processing, the results in AccuField View. Okay, now you ask, what are these softwares all about? Okay, Inspire Studio is a software where we can go from design to manufacture all in one single easy-to-use platform. It's intuitive and easy to learn with a nice user interface and unlimited construction history. We have free-form shapes, which I really like, especially when it comes to aerodynamics and to streamlined contours, which are not really simple like rectangular shapes and circles. There we have continuous NURBS geometry, where we can easily working there and adjust every small part. We have a sketching environment to create and edit 2D curves, and we can, of course, discretize these surfaces there, which then leads to a smooth transition to Virtual Wind Tunnel. Virtual Wind Tunnel is the pre-processing step. It's a vertical application tailored for external aerodynamic studies and designed with the user's needs in mind. The graphical user interface provides easy access to problem definition and solution strategies and is built up in a kind of streamlined workflow. We have an automated and customizable report generation that after every simulation, it runs provided consistent method for design evaluation. And therefore, here from Virtual Wind Tunnel, we directly export the DEX file to UltraFluidX, where we then run the simulation. UltraFluidX is the main heart or the main part of all this production or simulation pipeline. The tool predicts the aerodynamic properties. This technology is based on the lattice-Boltzmann method, which allows us transient simulation and also ultra-fast transient simulation results, which leads to super nice turnaround times that you can adapt every design change immediately. It's optimized for GPUs, you heard right, for GPUs to deliver extreme performance and to gain a lot of potential. The post-processing there, where we do an AccuField View. We can either do quantitative results by generating plots, diagrams, have a look at the boundary layer, and also visual analysis, like vector scenes, scalar animations. And of course, the fun part is not that short. There are renderings as well, where we can apply materials and backgrounds and have like nice pictures like here on the right. But let's have a look at how this really is all in detail. Right here, now you should see my screen closely. I've prepared a nice body geometry, which was sent in by Terrafenic. It's the Shell Eco Marathon team from TU Graz, which was so kind and sent it in for demonstration. First of all, I like to take you into the program, how it's structured and how the main control is. So if we click the mouse wheel, we can rotate around the center of gravity. If we move it, or we like to translate the image or the picture or the object, we can use the right mouse button. To select any, we just use the normal left one. Up here, you have the sketching mode, where you have a lot of things to do on. We just want now to dive into the curves mode to design a line on the surface. You easily click on the surface ribbon up in the corner here, and then you see all the spline locations already popping up. To have a bit of luck, we just start by clicking or maybe rotating it up here by using this upper top deck and then translating the model. Oh, he already did one. It was easily done by just pushing in or pressing this one and then designing the surface. Starting from this one, maybe to make it a little bit easier now, we may want to create a kind of hatch where the driver should be able to have his head in, that he doesn't be laid down the whole thing. So I think right now the driver should lay here. But to see the road a little bit clearer, it might be interesting to have a hatch or lookout that the driver gets a little bit more control. So let's do this. We have one curve already initialized up here. Now we need kind of to modify it, to get it to a really 3D model. So we click on modify up here, and now we can scroll through here, we look for the symbols, and there we find symmetry. That's what we need. We like to mirror that curve on the Y plane. And now I think it's still, you see there, when we just have a look from top, you see it's on the wrong way. So we click here on the blue point, and now we can enter the coordinates where the symmetry plane should be placed. So we like to have Y0. Easy it goes. There we are. Okay, done. We doubled on we symmetried the curve. Now we have I would say a contour where we could start to create the hatch from. It's a little bit streamlined already in the back, which allows the air maybe to go around a little bit smoother. Okay, now we like to extrude that one. Therefore, we can go on surfaces and then on extrude. Oh, now we already see some popping up. I zoom in here quickly to just curve. Okay, we click that. Oh, doesn't work. We do it in here. You easily can do it also in this side here, because then you have a little bit more control, and you can, then you don't have to, deselect the parts again when you are in the wrong part. Now I select the other one as well. There we are. When we now look for the front, you see it's not even, it's not symmetric to the y-axis, and this is the reason because we didn't select a reference direction. So I think they make it to normal to the surface in the first place, but now we can easily correct it by clicking Y. Or just moving that point further down here. Now we got this one. There we have the Y one, which can set it to 0. And now we are kind of, what we do selected here. Oh, we have something else selected, I see. Let's do this one again. We go from here, click on extrude, click these files. Now I got them. Now, okay, that was the reason why, because I selected already a geometry from that example model. We like to extrude the surface. Now we got it there. And this one, we got it as well. Great. Now still we have the problem that it's not really in the right direction. Now we can move it easily, turning backwards, and then get it controlled. I already prepared that. So let's have a look into how it should look like. Here's the hedge. And what I've already done as well is to mesh it to generate from the poly NURBS we use to generate a mesh from this one. And therefore you click on poly NURBS and go on NURBS to poly option to create this mesh. There you also have the possibility to choose a tessellation and all this. And then you easily end up the session and click on Save As to export the model. Then we go from the pre-processing step or from the preparation step to the pre-processing step where we set up the simulation. Here I just took the original model again and loaded it into the virtual wind tunnel with this import option. The controls in here are the same like in Altair software, and it's quite common to familiarize with them because it's just really these three options, like rotating it with mouse wheel, right click, translation, and that for selecting. Up here you have now the streamlined workflow I showed. So first, maybe here are some measurements and scale options where to move the object and to interact, and here are the options which offers by virtual wind tunnel. First, I'd like to offer or point out that it's really nice to have the model browser activated in the property editor as well. This shows us the overview of all parts and the property of the parts when we assign them. Let's start with to edit the wind tunnel. Now you already see that virtual wind tunnel already generated a nice and comfy wind tunnel for that object. First of all, I like to set the inflow condition. In this case, I like to have it 40 kilometers per hour. I don't know how much this is in meters per second right now, so just enters like this. Oh, no problem. The software directly transfers this kilometer per hour ones into the meter per section SI unit, what we choose down here. You could also alter it to different other things if you are in parallel system, something is just adapting. Now we like to check the dimensions of the wind tunnel. We could change it here, but I think they are all right for us now. Okay, wind tunnel in place. If we like to move the car a little bit backwards, we could just use the move option, but I think this looks good in regards to distance to the inlet. Now it's time to identify parts that Ultra knows what really matters about, and what is the part and what's maybe a wheel or something else. Therefore, we just click Identify Body. Body, that's one. Okay, done. Now I unblend the wind tunnel, which you can do here by just clicking on this icon. Now we like to identify the tires. So we click on Identify Wheel, and now we click on the wheel. They pop up in red. And as well, you recognize, right? The symbol here changes as well. And when I go through them, they now light up a little. Okay, going back to a good view. All important as well is to make sure that the normals point outwards, because Ultra is determined on this normal information. It's determined where the fluid should be, if it should be outwards the geometry or inwards the geometry. Therefore, just click normals. Normally, all the parts should light up in the color which belong the normal direction to, but if not, you can just select the parts by using the mouse tool I have here. We see already that we have all outward turned normal, so we're good and ready to go. The wheels as well, as you see here. Okay, the pure simulation is set up. Let's put it back in the wind tunnel. We could run this now. The thing is that we now have a unified mesh. We have the same voxel size everywhere, And to have a little bit more adaptive one, we could use some more mesh controls. The far field walker size, so that one in the wind tunnel, is listed here. It's on 0.2 meters. I think it's quite good value to start with and to have a look. The other things you can put here would be a rectangular box refinement, offset refinement, or even a custom refinement when it comes to tires, mirrors, or everything else. So let's do a box refinement for that body. You click on the box one and then click on any location on the body to create a refinement box. So it's quite helpful to have this information here. Thanks. Refinement done. We can alternate the level a little bit. We just had level 0, that's a wind tunnel, so we would start probably with level 1 to make it a smooth transition. The offset one would work similar as well as the custom ones. I prepared already, and I would like to show you the option here that you are able to import mesh settings or simulation settings when you do a design study. You don't have to set up the simulation all the time again. So you can just load in the new geometry, and then you can go on template, so file, template, and import what you ever like. And also you can export the settings, but we like to import them now. I take the full one. So here's the full simulation. It's an XML document where all the settings are displayed for Ultra, and we just click on open. Oh, suddenly, tick, it's loaded, and now we got some mesh controls imported. Here we got now the rectangular shapes and the offset shapes. The offset refinements are shown due to this. You see now the offset between this and that. Well, I can maybe just highlight it a little bit more. Oh, now it gets stuck. Yeah, that's how they are made. So the first one, the upper one here, there's a body one, and the other one is a part-based one, which is really just directly only on the body. The other one is rated on all parts. Having the mesh control done, and I really come back to this and point out some guidance material in the later slides, we need to set up the material. The material determines, of course, how the air is, how heavy it is, how viscous it is, what temperature it has. And here we need the specific gas constant again, because in particle-based solving, this is the main important. When we get it all done and we are ready, we just click on the play button here to export the right to UltraFluid X. We can put in a name, check the runtime. I think it's computed automatically. Every time when you see these flashes, you can just auto compute them, and then you're ready to run. You export the mesh. You can select that to have a look at your mesh, and then you can export, and Ultra can, and that can be loaded up onto the cluster to run on the GPU cards and perform the simulation. So let's dive back into the slides to really have a look at how we could perform a good simulation, and what are some key facts we should keep in mind to achieve a good simulation setup. And I like to give out some iteration values where you easily could start with when you do your own ones. So let's head into the PowerPoint presentation. I think you're already there. I'm still on the program, but I'm also back there again. So let's hit to the next slide. How to set up a CFD. Let's give some facts. So first of all, I like to regather the surface mesh requirements quickly. We only need triangular elements. The element quality is of low importance, and part intersection is allowed. That makes it quite helpful, I think, especially when you have cut problems or something where you have some small interactions. Ultra is fine. It only needs the normals of the surface must point outwards. What's recommended there is to have a closed and watertight mesh, but I think in some cases Ultra will try to handle it as well. If there are some small cracks in the mesh or in the geometries due to cut problems, it doesn't really matter for Ultra. You could try to run it still. Now we import it to wind tunnel, and we are setting up the the computational domain as well. Here's some guidelines. First of all, it's important to understand that voxel size, number of iterations, determine the computational time significantly. So in general, 30 to 50 flow passes are suitable to reach convergence in automotive setups. One flow pass refers to the time it takes for a single fluid particle to completely stream over the entire body of the car. So if we take now the cursors, so what I really point out here is if we change the cursor's voxel size, we can have huge influence of the computing time itself, especially also for the iteration steps. When we have 30 and then to 50, we extend the computing time significantly. The cursor's voxel size in the far field, we already have that, should be around 0.2 meters to 0.05 meters. So 20 centimeters to 5 centimeters. For me, 19.2 centimeters is a good number. You will figure out that later after you set up your simulations. After a while, you figure out why it's a good one. The simulation domain should have a blocking ratio around 0.1%. So by blocking ratio, I mean that's the projected area of the vehicle divided by the area of inflow of the wind tunnel. To give some guidelines here with respect to vehicle dimension that you can easily adapt them, I have plotted this nice graphic here on the right, which says that you should have 10 vehicle length to the front and 30 or 20 vehicle length to the back of the wind tunnel. You can easily adapt that to your setup. Finishing up this far field from relative coarse Cartesian background grid, what we already had, to the mesh is consecutively refining towards the surface. The outer level are typically defined via boxes like we already had, and therefore I proposed some refinement guidelines as well. Here on the table, or maybe first talking about that we have rectangular refinements, it's now made of interest what we like to achieve before we start talking about the guidelines and numbers I would advise you. So we like to achieve around 3 to 6 millimeters at the boundary to the geometry. Usually it takes around 8 refinement levels to get there. And these guidelines here I wrote down are also in the same format we had on the last slide. So in refinement level 1, I would like to have 10 length to the front and 20 car length to the back. So every time when it's in bracket, the first number is to the front, the second is to the back. But attention, when you customize these refinements, make sure that you think about that time stepping on refinement level 0 yields to adequate sub-time stepping in refinement zone. So it means that one time step on refinement level 0 covers or implies 2 time steps on refinement level 1. If you're on refinement level 0, 1 time step in refinement level 2, you have already 4. So you're always to the power of 2. And this causes an oak tree-based 2-to-1 refinement technique. And that's also why I take always the far field voxel size of 0.192 meters, because it fits nice in this row of 2 to the power series. And you can easily separate it by 2 or divide it by 2 and get a really nice numbers again. The same yields for 0.2 as closest level as well. Now we come, by using these numbers, we come closer and closer to the surface. And as you see, the dimensions get smaller and smaller. All dimensions are in respect to the car center of gravity. So if we come closer to the surface, we need a higher refinement. And therefore, we could either use offsets or custom volumes. If we use a part-based refinement, so an offset volume, these might be an interest when we have high shear parts that are suitable to place them. So here on the left, the whole body show quite high stresses, especially on the wheelhouse. Those regions with these high stresses, there is a lot of turbulence appearing close to the body. So they show a highly transient character there. When we now look at the picture on the left, we see the transition from the top, from the coarsest mesh at the top to the fine mesh wrap kind of thing around the body. And this is really where it comes to the point that we only have a cubic size mesh here, which is totally Cartesian, and then we get closer, then we get a wrap kind of thing, which is then basically produced by the part-based refinements. Instead of defining these wraps, we could also use a custom mesh as well, or custom refinement control as well, like in this part here. The predefined custom refinement zones can be adapted to new similar geometry using morphing like in Inspire Studio. And there's an option where you can, for example, generate such mirror volume to refine it around there. Or in the animation up and down, you also have the idea of making the tire custom volume control. With this, you can, with the extended region, you can fit in the whole tire weight, and in the end, you gain more accurate results and probably get a more efficient aerodynamic setup. Regarding tire, there might be some additional information interesting for you. The outstanding wheels often shown on Shell Eco-Marathon vehicles, and its influence should be analyzed a bit in more detail. Then I would advise to use Altair Radius, the solver, to create deformed tires, and then get your aerodynamic package even more realistic and in the end be more efficient. If you now had any questions or questions to the guardians in this place in setting up this simulation, I know there's a lot of input. Please use menti.com to dial in the code 220330 and ready you go. We will try to handle all these questions in the setup later with Norman in the Shell studio. And if you can't wait, beside this, there's also an ebook available which covers this guide in detail. So don't hurry, just keep watching here. There's everything planned and you have plenty of time to read through this material, and I guarantee it will probably answer all questions. As well, if not the case, there's also this recording will be online or another one, but there isn't recording online and you can come back to these results, post, have another chat with yourself or with your mates about the slides, and then you can easily set up your own simulation. But now let's jump back into some results and have the interesting part continue. So I set up a simulation, like I said, and my idea is to have this lookout for the driver, maybe the hatch or something in the custom case there, and a flat front bumper to add cooling inlet, maybe for the battery or fuel cell. I thought it's maybe kind of a good idea. So I run a simulation, and now we'd like to have a look on the results. When you look on the results, there's exact stepping you should follow. So first of all, you should look on the computational time if it makes sense. Here I just popped up some values I ran the last days to really present you guys. As I already said, UltraFluidX needs GPUs. So I just ran on 2 clusters, one's with the K80 graphic card and the newer V100 graphic card. These are 2 models just to give you an attention how this could feel and how much runtime and RAM and memory the machine should have. On the few older resource, the run case around, what is it, like 43,000 seconds. I just calculated quickly, it's around 12 hours, I would say. And on the newer one, it's around, let's say, not even an hour. In both cases, the implementation achieves of ultrafluid X achieves the same coefficient and therefore the same result quality, of course. But now looking at these simulations, so we made sure that the runtime was okay, not especially high and low, and now we have a look how the simulation procedure was going on. Therefore, it's good to look at the progression of coefficients. So in the first time, we have launching up sessions here in the images where we see it ending up with a high peak. This is where the flow got accelerated from 0 meters per second to 11 meters per second. That's what Ultra does. And we see it later in animation how it looks like. Then we have the transition peak where the flow switches from laminar to turbulent flow. And this can be spotted quite good here. Then we already see that drag is nearly constant. The solution, I say, is probably convergent. The lift fluctuates a little bit more around the mean value, but in general, the conclusion is that the simulation is worth to post-process here because the results here looks quite good. Okay, let's dive into the drag and downforce thing. So taking the average for the last iterations, we see that we now have the coefficients of lift and coefficients of drag available. This coefficient of drag differs about 0.023 and the lift about 0.354. So both of them got a bit high. Now we have the animations here on the side, and you see that the flow is starting now with is really flowing. It's a transient image, and when it's like flickering in green, then we see that's the start where the flow starts, and then we see building it up more and more. This is then how the results look like due to this transient code method of Lattice-Boltzmann. As we see in the animations, most influences are coming from the front bumper. We see the big pressure zone up there, or even especially here, the velocity displayed. We see low velocities there. And also over the roof contour, it's way more turbulent, especially behind this hatch thing. To confirm that assumption, let's have a look of some less visual results, more some quantitative tools. The sectional drag, of course, it's part of this study today. The sectional drag generally is created by slicing the vehicle up in 100 sections, or if you choose, you can do more. I did 100 here. And for each of these sections now, drag and lift get computed. High influences can be spotted easily by peaks. For example, in the custom case here on the right, we have huge drag at the front bumper. You can spot it. We just start by slicing, and the first slice has directly a huge intake. As well, the increase of lift, what we see at the hatch kind of lookout thing up there on the top, we see the blue bubble which was building up. When we now look on the custom case and on the initial case, we see that in the front tire housing, the wheel housing, we see that the drag value is also quite high around that region. We should talk about this one later. But first of all, I'd like to introduce another version to see at these sectional drag plots, especially when it comes to the cumulated representation. The cumulated presentation is not now displaying all value in its own. It's summing up all the slices until we reach with the last slice, we reach the results of coefficient of drag and lift, what we get as information from the results, the average ones. Here, the strong gradients indicate the major influences. And here it's nice to see that also in the hatch and lookout thing, we have in the custom case on the right, we have the highest gradient there. Oh, I see you. There we are now. Okay, we got the cumulative representation, and we have the custom case, which is on the right, where we have a strong gradient. And here in the cumulative representation, we have to look out for strong gradients because they indicate the major influences. Offset in drag, we also can predict quite easily. we start the value in the custom case, which is way higher than the normal case. And also in the changes on the roof contour imply huge lift changes, like we see the lift in the custom case just roughing through the roof. Maybe the body changes I performed haven't been that suitable. But let's determine this in the last step to look at the drag per part values. So here we see that in the initial case, the body determined 90% in the overall drag, and now in the new custom case, we have 91. And therefore we can say, of course, that these changes I performed are directly determined by the flat front bumper and this hatch lookout thing. So what are the lessons learned from this one? First of all, maybe the design was not that suitable. So it's suitable or it's recommended to go back to the last iteration, to the flat or to the more streamlined front bumper is more optional. And also the lying driver position allows a more streamlined design. What could be tested in the next cycle of iteration would be to adapt to burr holes of a Hamburg wheel, maybe here to do some bioengineering influences on the wheel housing to decrease the drag there. You already covered down the wheel house down to the ground to leave less attack to the wheel itself. But maybe this would be an idea to test out. Finally, there are some things you should definitely take home, what I really like to point out here. Learn from the tests you made. Improve and try new concept, like here, this bioengineer thing. Why shouldn't try it? It's fast turnaround alternative, and maybe you could spend these hardware resources to get some more clearance there. Use the post-processing technique I showed. Do not only trust in nice and colorful pictures, these animations. I know they look quite good, even in these transient cases. But the plots and the diagrams, they really show the true findings and the true things what you can say about your design approaches. Okay, and what about the tools? Is there as well a lessons learned, something you could take home with? Of course there is. So, summarizing it all up. We got short preparation time for the surface, which is really nice. We got automated volume meshing. Oh, that's also awesome. And we can perform transient aerodynamic simulation. We can adapt to quick design changes, and we have a simple workflow where also the intuitive GUI helps that new teammates or new person can directly work into that. And the fast turnaround times allows us to adapt to all trends. Summarizing that is they are easy to use and you save a lot of time. And I know from my similar student days that sometimes time is the most valuable good in project management, to get the car ready and the time to go with the car on the next big event and compete against the others. What we hopefully can do next year again. But now, just summing it all up, how to get started, maybe that's a big question for all of you, and like to postpone it to this, prepone it to this slide. So first of all, as I already announced, we published an ebook which summarizes all content you heard the last hour. Download it. It gives theoretical and practical advices and the guides I showed. May they help for doing the first steps. You can get that one on altairuniversity.com. Sign up there for the student edition as well to get access to the products. If not happen, try to get a sponsorship for your team, which is also quite a nice tool to have to get access to all the software. Get in contact with Altair universities. We are still working on getting some benchmark GPUs to run servo tests for you. Reach out to your global Altair or to regional Altair team to create these next steps and to get in contact. Especially here, I like to point out that some universities you might add, they already setting up GPUs. So it might be an idea to ask your professor and check out the situation locally. So probably you already have some GPUs up and you could start running the next days. It would be really nice to see some result out there. Let's round the 7 up. Last but not least, I like to give out a big thank to the Shell Egg Marathon teams from TU Graz and Duke University for sending in their racer geometry and make it possible to show these hands-on cases here live for you. I hope you liked it, and I hope you tune in again to the next seminar, which will hold. It was a pleasure to me, and now I give back to Norman. He's in Shell Studio. Back to you, Norman. Thanks.
Thank you so much, Paul. And I like how you refer to my home, the Shell Studio. That gives me a completely new idea. What else am I doing here in future? So thank you very much for the very insightful and for the very detailed presentation. It was interesting to watch, and I really enjoyed it. So for everybody
Thanks.
joining us on this call today, can you please now submit all the questions that you may have? This is your chance to ask Paul anything you might like to know about aerodynamics and how to calculate it. Please go to menti.com on your web browser and enter the access code on the screen, 220330, and that's not the winning numbers, that's the passcode for menti.com. Or if you are struggling with Menti, you can also type your question in the comment box on YouTube when you are logged to it. First, Paul, to ease you in before we get to the really hard technical questions, can you tell us a little bit, what are the first steps to get going with Ultra Fluid X for my vehicle? How do you get going?
Yeah, really good question, Norman, and maybe a good question to summarize this again. So the first thing maybe you should really do when we can maybe have slide 50 back up again, which is also a good summarize of all we should keep in mind. There's an ebook out there what we published which summarizes all that content. That's what I already said, but I can say a little bit more about it. It's dealing about a Formula student team who's getting the first hands-on experience to Ultra Fluid X. So it was, or it is, in the same role where you are now, and this book has been a guide for them, or has been an idea and shown their problems and their ways to set it up. Easily downloadable as a PDF to read at home or on the way to school, or even in your, I don't know, out in the sun in some days. That would be maybe the first part. The second part is to really sign up for a student edition or a sponsorship to get the software. And the third part then is to get GPU machines and just have a run with these settings I recommend in here. Watch maybe the webinar again. It's still available, and I think then you should roll pretty good and smooth in the first steps.
I think I always knew it, that the answer to fluid dynamics and understanding is having a good read in the sun. So thanks for pointing to the right sources here and the right resources. We had also a couple of questions coming in, if this presentation will be available later, or how we can get this PowerPoint presentation. Yes, the presentation, including the PowerPoint, will be available later. You will be able to watch the recording, and the way you registered for this webcast, you will be receiving a link to the recording, so you can watch it as often as you like, and also you can share it with your teammates, or you can share it at your university to anybody who might be interested in hearing more about Shell Eco Marathon, or about the topic, of course, about fluid dynamics calculations. Now getting more to the practical hands-on questions. A question that has come in is asking, how can I model rotating wheels? What approaches are available?
No, that's a wonderful question. I was looking out to that one. Their serval approach is available. we just use in this webinar a quite simple approach. We just assign the velocity or a rotational speed onto a wall of the tire, so on the tire itself. So every particle which now touches the tire gets accelerated in a different way than instead of touching the body. This is one approach. Another approach would be a little bit more complex. And when we think about that tire slide in the beginning, what we had on in the theoretical part, where we spoke about the complex flow, this is maybe the approach you would use to really model tire dynamics and tire fluid dynamics. It's called the multi-reference approach, multi-reference frame approach in total. There, we also have that rotating wall or this moving wall on the tire itself, but we also can point out a volume in the rim normally where the particles from Lattice-Boltzmann are influenced by the tire rotation itself. So we get a more accurate and realistic behavior of the air in these tires. Therefore, you have easily to set up some really, some volumes, some particle volumes in your Inspire Studio, and then you can assign the MRF function to them. All this is written down in the ebook, and it should definitely guide you through.
Okay, thank you. And yes, you already answered the following question. How can people add the moving reference frame at the wheels? Next question that has come in. How accurate must the data be for my car body to start a drag simulation?
Depends on what you like to achieve. If you are in the high-end efficiency class, and if you're really thinking about reducing the drag around 0.1%, of course, then the educt, let's say the model, what you load into, is the main or has a main role in regard for the result in the end. But if you are just taking the first steps, it might also be okay to start with simple geometries, having maybe some spinning circles, some cylinders as wheels, a big rectangular shape as the body, and then to start to iterate more and more until you get to the solution.
Mm-hmm. And here's a very interesting one. Maybe you understand why this would be relevant, but one of our viewers is asking, can you define the material as water?
That's a quite interesting thing. The thing is, when we dive into some theoretical knowledge about ultrafluid X, that ultra only handles low or not even really compressible medias. And when it then comes to water, it looks a little bit different there. So in air, you generally say you have to have the Mach number. I think the student who asked me can also refer to that as well. And in knowledge of this theory. So if you have the Mach number and the Mach number goes beyond 0.4, the fluid is not really incompressible anymore. So it gets compressible then, and the physics totally change. When we take water now as a fluid in ultrafluid X, the main purpose of ultrafluid is maybe a little bit violated. Ultrafluid is mainly scripted for, mainly published for external aerodynamics. So I think you probably wouldn't get the right numbers there or even error codes. But if you want to play around with that, give it a try.
Okay. Another question is on the wind tunnel identify parts, the wheel section, there are two different options. What are these two different options for? Or what's the difference between these two options?
Yeah, good question. Maybe we can jump back into the presentation option and have a look at the software icon to really make sure that you all understand or all see also the visual things about identifying powers and to get you all catched up. So up here, the student is talking about those ribbons up here and about the identify part ribbon. When we click on that one, we can first identify the body, like my mouse is now showing it. When we click on the heat exchanger, then we see identify heat exchanger. So we can select an inlet, a frame, and an outlet. So due to this, Ultra then knows where to imply or where to add a pressure gradient, which is then calculated based on information you have to enter here. So when I click, we don't have this yet, but it is covered in detail in the ebook because there we use from the student car. And of course, it has some heat exchangers because it was kind of the full geometry. Then you can have a look in there. Another point would be to identify wheels, what I already was talking about. We have the wheels here, just the rims and the tires. And here you see a little, it's not really clear to see that we have the rims, the tires, and then the small gaps between they are closed. And that's where you should place the custom volume to have the multi-reference frame interaction on the particles there. So I think this is a good roundup for all the things. Here's another good option. When you look at there, you get shown which part is identified as what and which is looking like. How is it looking like when you see? Imagine now you have a huge assembly, around 60 parts, and you sometimes lose yourself. It's a good one to refer back. Yeah. I hope this makes it way clearer now.
Thank you. Yes, thanks so much. Just would like to remind everybody, we still have a bit of time left and a few questions also. But if you have any questions, this is your chance, last chance. Type in the questions in menti.com or in the comment box on the channel. If you want to ask Paul anything about these calculations, the software or the aerodynamics, please do so now and I will include your questions. Moving on for now, there are a couple of questions around the computing power behind running the software. First question is, what is the minimum PC requirement to run the wind tunnel?
The good thing in Altair products is that they are mainly developed for all kind of computers, laptops, and so on. I especially had a friend of mine, he was running the wind tunnel on a small, like these Microsoft Surface things. And I can just point out that, of course, the more power you have, the better runs everything. But for this simple cases we had a look at, I think you are able to run it nearly everywhere. When you're done ending up, at assembly with like 100,000 parts, or probably quite a lot, but then it's going to be interesting. Maybe if you have a little bit more RAM, it's a little bit more fluent and makes more fun to use.
Mm-hmm. So nothing beats PC power in the end.
Yeah.
Is there any software for Macs, for Apple Macs?
I think I have to refer there on the website of Altair, and you should check it. When you go on Altair and then of Virtual Wind Tunnel, there should be some requirements the machine you will like it running on should have. I know that, for example, UltraFluid X, it runs on the cluster, supercomputer, and for Mac there, of course, solutions to enter these cluster computers by terminal. The virtual wind tunnel part, as I said, you have to check on www.altair.com on the products to make sure. I know that there is a standalone software for Linux, and for Windows.
Okay, thank you. And back to some technical questions presentation. Can we use the aero loads as a boundary condition for a structural analysis is being asked here.
Oh, yeah. Important question, I think, especially when it comes to kinematic design of the vehicle and designing all the parts of the drivetrain. There is an option, but it's still under a work in progress. We work on an aero load mapping onto FE models. So stay in contact to that.
Yeah, thanks. Work in progress. And somebody also asking here, already bid for the answer, but obviously to see what is in it. How much drag reduction can I expect when removing the two side mirrors from my car?
Well, that's going into detail. Well, if we are talking about a passenger car, then we probably would say it's around 5 to 10 counts. Just to make clear what I mean by saying counts. So in aerodynamic language, a count describes 1/1,000 of, for example, the drag coefficient and the lift. So if I say it changes around 5 counts per drag, then I mean that we gain 0.5% less drag overall. So I think it's like, to just summarize, it's around 5 to 10 counts.
Mm-hmm. Okay. Now we're coming to a question that is, I wouldn't say for the faint-hearted, and certainly it pushes me beyond the edge, but I'll read it out to you, and I hope you have the answer for it. The LBM,
Okay.
the LBM is intrinsically transient. Are RANs available if one requires simpler steady-state results?
Yeah, that's a good question. That's a really good question, because this person likes now to go the other way around. So to use the LBM, the accuracy, and to gain then a steady state solution to achieve that. Of course, the Lattice-Boltzmann method is transient by nature, but there are options available that you can, of course, look only at averaged results. So if you go in virtual wind tunnel and then set the average window, so kind of low passing filter, up to the maximum number of iterations you have, and then put out the iterations in the last step, you gain exactly these steady state results what you were looking at. And this is quite nice to have. You're still transient, and when you then see in this trend, in these steady state results, that you like to have maybe more transient information, then you still have the transient information available. If you get just not the average frames which are getting out there, so if you have just the transient solution cases.
Okay, thank you. And what size do result files typically have? So how big are they for download purposes?
Wow. Okay. Yeah, guys, you're doing good in this question. I like that. Please keep posting to menti.com. That's fun. When we speak about download sizes, so a case like this one we had here, it could end up around 10 gigs, 10 gigabytes. But when it gets really huge and you have a lot of transient snaps what you take, so you can maybe, if you have 16,000 iterations and around every iteration you put out one snap of the whole domain, then you probably would end up 200 gigs. So quite a lot of data. And that's also the reason that Ultra also needs a lot of RAM to really get running good. But I would like to point out when you are at uni or close to the cluster itself. For my days and from the student, it was like this. We had a small office near to uni and had a good connection to uni, so it was possible to work directly on the server, and so you didn't have to transfer all the data back and forth. You could work it right there. I'd like to point out the X11 forwarding. I think all the Altair products support this one. Maybe also an alternative for the Mac user that you install with the wind tunnel on the Linux machine and then use X11 forwarding on SS hardline to get the display hooked up to the big cluster one.
Good tips here. Good thinking. I have a couple more questions for you. So last chance, if you want to ask anything else or anything is triggering your thinking while you listen to Paul here, go to menti.com and send us your questions. Somebody's asking, how did you get your computational domain dimensions?
Okay, how I did them? I think you mean those ones I show on the guides, on the guide slides. Maybe we can have up this one again. Give me a sec to get everything organized. The days before I was at Altair and I was working at uni and doing my bachelor thesis, I spent quite a lot of time to look into scientific paper and to have a look on Ultra. So now we should have the slide coming up directly here, and we can look again onto the dimensions. The 22 width and 20 height and all those are the results of my bachelor thesis I did here in the Institute of Computational Fluid Dynamics, or more for for fluid dynamics itself. It was a half a year work. We had some wind tunnel experiments, and I was working quite scientifically to get these optimum dimensions. They are just my ones. I think they're not scientifically proven, but I think they work really good. So as a kind of own opinion on this, that's the story behind. And I think you should also try to alternate them. So if you like to get a little bit more efficiently, then just shorten it up. And I think you should get a feeling for that. Yeah.
Okay. And another question on the software. Can I do thermal analysis or even water cooling with this software?
Okay. Now that's interesting, because I think the same yields for Formula Student. We had the point there as well, where we had like the cooling systems, and then we wanted to set up a whole simulation with CFD and of course the thermal effects covered as well. I have to point out that badly that there is no option in Ultrafluid X. Ultrafluid X is only capable to simulate external aerodynamics, but therefore in a really accurate and of course a transient way. But if you like to do the thermal part a little bit more, you should definitely have a look at AccuSolve, also an Altair solution, which is capable to do CFD enabled strokes simulations and of course plugged in thermal simulations.
Okay, thank you. And last but not least, a question that is probably related to many of us. Is the software available in other languages?
Oh, yeah, of course. I directly can point this out. I think, I never went through the whole list of languages you can select when you're installing it. I know that there's German and English. That's what I use, but there's French and I think some, I think you will find what you need. Of course.
Okay, well, that's a word of confidence about the language packs available for this software. Well, I think we've spent a good 1.5 hours here today, and I think we are running at this point out of questions. I would like to thank you very much, you and the whole team from Altair, for the time and for your efforts that you spent with us here today to run through all these questions and give us this amazing presentation. Thank you so much. And hopefully you will have a good rest before the next presentation that we have today. But thanks again to everybody here on the line today for joining us and for taking part. There are more virtual sessions coming up later in May. So if you haven't registered, so please go to our website. We would love to have you join us on our next upcoming learning sessions. And until then, thank you very much for joining us and have a great rest of the day. Bye-bye.
Thanks. Bye-bye.